the extraction of metal using a reducing agent and applying this reducing agent on an oxide. The question comes in mind that is it the only way that we can extract metal from its ore? Answer is no, yes, there are other alternative methods also where you need not to make oxide and use a reducing agent like coke, but electron is a reducing agent and these methods where electrons are reducing agent, they are called electrochemical methodology of metallurgy. So, in this case electron can be produced either in a solution or in a molten state of the salt. So, electrolysis is carried out, you know very well that in electrolysis electrons are easily produced. So, electrolysis is carried out in solution or in molten state and reduction is done by electron of the matter. So, obviously for this kind of reduction you have to use the relationship between delta G and electrode potential. The delta G naught is related with the electrode potential by this equation. In this equation N is the number of electrons required for reduction of a metal. For example, if you have iron 3, then for one atom of iron 3 plus or one ion of iron 3 plus you require 3 electrons. So, the value of N for such a reduction will be 3. For copper 2 plus the value will be 2 and what is F? It is Faraday, it is its value is around 95,000 and it is for required for 1 electron reduction process, the charge in coulombs required for 1 electron process. Now, this E0 is very crucial for electrochemical methodology of metallurgy, because if this E0 is negative then delta 0 will become positive and the reaction will not become not impossible or non feasible. So, E0 what? Redox couple formed in the system, because whenever there is electrolysis there is a some at one electrode electrons are produced, at another electrode electrons are absorbed. So, obviously this whole makes the redox couple and if the E0 is negative, such metals are called more reactive metals, reduction will be very difficult. So, for application of this electrochemical method of metallurgy, the essential requirement is that E0 values of the redox couple should be positive. If it is positive, it will give the delta G negative and the electrochemical process will be feasible. So, this ultimately boils down that very reactive metals will be difficult to reduce at a, they will be required, they may be requiring very high potential or it will be difficult to reduce them, but those which are less reactive can be easily reduced. Let me give you an example. You have copper, iron, copper, iron 2 in this reaction they are written. More reactive metal, iron is more reactive than copper. So, it goes into the solution when this reaction happens, and if you take say for example, here in place of copper sodium, this reaction cannot happen, that is sodium plus iron. If you want to carry out this reaction, this reaction cannot happen, because the metal is more reactive than the iron. So, iron cannot reduce a more reactive metal, but it can easily reduce a less reactive metal, and copper is a less reactive metal. So, in electrolysis the copper ions are discharged at negative electrode, which we call as cathode, and deposited there, whereas iron goes into the solution in place of copper. Now, the best example of this electrometallurgy is isolation of aluminum from its ore alumina. Now, alumina as such cannot be dissolved in any solvent, because it is refractory material. Refractory materials are those which cannot be dissolved in acid easily, or they can be dissolved in base, but with difficulty. So, what we do? We dissolve alumina in calcium fluoride and a complex of aluminum with fluoride ion. Now, this brings the conductivity into the melt, and this also dissolves alumina. So, alumina is in a molten state. By reacting with them, the alumina is in a molten state. Now, this fused matrix is electrolyzed. How electrolysis is carried out? This is carried out in a cell. The diagram of the cell is shown. It has a carbon line steel container which has carbon line, or carbon line containing a steel container, and this acts as a cathode. Now, we have anode which is made of graphite. We have a anode which is made of graphite. Graphite is a carbon. So, carbon anode is there. In a commercial setup, several such electrodes are used, because electrolysis is carried out at a very large scale, and when the electrolysis is carried out, aluminum is formed in a molten state, and from here, from this outlet, aluminum is taken out. This process is called Hall-Héroult process, and if you look at the overall reaction which takes place, is alumina is reduced by in fact carbon into aluminum metal, and carbon dioxide is a byproduct. Now, the oxygen which is liberated at anode, it does not go in the atmosphere just like that. It reacts with the carbon of anode and produces carbon monoxide and carbon dioxide. So, in this electrolytic process, you will notice that real reduction is done by carbon. The process is basically is based on the electrolysis, and if it is calculated that for each kilogram of aluminum which is produced, how much carbon is burnt? It is around 0.5 kilogram of carbon from the anode which is burned for each kilogram of aluminum. The electrolytic reactions which occur at cathode, aluminum is formed, at anode it is formed, and these electrons which are liberated here, they are used here to reduce aluminum ion into aluminum metal. Now, there is another way of extracting metal from the ore, it is called hydrometallurgy. It is used for low grade ores. What are low grade ores? Low grade ores which have less percentage of desired metal. If there is a copper ore, then desired metal is copper. So, a low grade ore of copper will be having less percentage of the copper which is present in good ores. In such cases, first is you have to concentrate the ore, and ore is basically for concentration is leached out with acid. What is leaching out? Leaching out, it is continuously treated with acid, so that in a form of salt it passes into solution. Now, when the solution is enriched with copper, say for example, in this particular case, then the copper can be reduced with the help of hydrogen directly, or copper can be reduced with the help of a metal which is more active than copper. So, more active, you have learned earlier that iron is a more active metal than copper. So, if the iron scraps are added to this copper solution, the copper is reduced and iron goes into the solution in the form of iron. Because this, whether a metal is more reactive or less reactive, this is given in electrochemical series. Those metals which are above a particular metal, they are considered to be more active. Those which are below, they are considered less active. So, in the electrochemical series, iron is present in case of above the copper. A question may be asked that there are other metals also which are present above the iron, why iron is chosen? I just explain you. Zinc is another metal which is above the copper, can be used for reduction of copper ions from a solution into copper metal. But if the reduction is carried out with zinc, reduction is also faster, but here the economics decides that which metal has to be used. Zinc is much costlier than iron. So, using iron scraps is economical, that is reason that commercially iron is used to reduce copper ions from a solution in hydrometallurgy. Now, so far we have been talking about reduction and you showing that giving an impression that reduction is only possible way of getting or extracting metal from the ore. It is not true. For extracting element or for isolation of elements in general from any source, oxidation is also or may be used. Oxidation is a possible method and may be used. It is more suitable for non-metals. Now, chlorine is very widely used to disinfect the drinking water. In all water supplies from the municipality, the chlorine is used as a agent to disinfect the water. So, water is chlorinated. So, chlorine is required in very large amount. The biggest source of chlorine is brine. What is brine? Brine is basically sodium chloride solution is called brine, and the sea water is effectively a sodium chloride solution or called brine, it may be called brine. Now, this chlorine, if it is oxidized, it gives sodium hydroxide and chlorine gas. If this brine is electrolyzed, then chloride ions are oxidized and result in chlorine gas and sodium hydroxide, or the solution becomes alkaline. If you look the feasibility of this reaction, you see the delta G value. Delta G value for this reaction is positive. So, if you want to make the delta G negative, in this equation you have to use a E0 negative of the order of 2 volt, and so if you use an external EMF which is greater than 2.2 volt, the chlorine from the brine solution can be oxidized. The oxidation is not limited to non-metals. It is also known that some metal may be obtained from the ore by using oxidation process. Silver and gold, these two precious metals are present in the earth crust in native form. What is native form? Native form means that they are not in combination with sulphide or oxide, just free gold and silver, some dust or some rocks may be around them. So, they are leached with cyanide. What cyanide does when they are treated with cyanide? Cyanide oxidizes them, both gold as well as silver. Now, this metal by oxidation of cyanide comes into a complex form. From this complex form, they can be obtained back by using zinc as a reducing agent. You can get back copper. So, zinc acts as a reducing agent. So, basically the oxidation process is involved in overall extraction of metal for ores, from ores in these two examples, silver and gold. Ultimately, we have obtained the metal by using a reducing agent. This is unlikely in case of chloride, from where we are getting chlorine directly by oxidation. Here we are using oxidation as a supporting procedure. Isolation of metals has 3 steps. We do this isolation from ore. So, first step is convert this ore or dress up to a form convertible to metal. Convertible form is oxide. The next step is convert oxide or other form suitable for conversion to metal. At this stage, the metal which we get is not pure, it is impure metal. So, what to do? To improve its purity, you have to refine it. So, this step, which is called refining of metal, is very important to get the pure metal. So, metal extracted by any method using any reducing agent, using electrolysis or any other method is contaminated. It is very important to note that it is contaminated. To prepare metals of high purity from this contaminated metal is called refining. The question may be that can there be a universal method for refining? Answer is no, no universal method. Then how we decide that about the method for refining? To decide about the method of refining, we have to see the properties of the metal and impurity present, because from different ores the metal extracted may have different impurities and different kind of metals may have different associated impurities. So, two things are important: properties of the metal and second the impurity which is present. Now, they vary from the source of the metal extraction as well. Some generally used techniques for refining are distillation, liquefaction, electrolysis, zone refining, vapor phase refining, chromatographic methods. So, depending upon the nature of the metal, we can use the method for refining. So, the first is distillation. Now, this distillation, obviously you know that you must have used distilled water. Then how we get the distilled water? We boil the water and collect the vapors. So, for applying distillation to the purification of the metal, the important criterion is that boiling point of the metal should be low. For example, of zinc or mercury, you know mercury is liquid at room temperature, its boiling point is low. So, just like water, we can convert some higher temperature than that of water, mercury into vapors. Those mercury vapors can be condensed into the form of pure mercury. So, impure metal is evaporated and pure metal is obtained as distillate. Distillate term means the vapors are condensed to liquid form. Vapors are condensed by cooling to liquid form. We call that the liquid as a distillate. So, for application of the distillation, the essential requirement is that low boiling point of the metal. So, it has a restricted application. It cannot be used for any kind of metal, but only for those which have low boiling points. The liquefaction is used for low melting point metals. What is done? In fact, the metal is converted into a molten state and then it is allowed to flow on a slopy floor. Slopy floor means just like that, slopy floor. It is allowed to flow on this kind of slopy floor. So, what happens that the molten metal runs down the floor and the impurities which have not been melted or which are solid at that point, they stay back on the surface and metal which is in molten state rolls down the floor. The example is tin for this kind of purification. Now, for liquefaction also the essential requirement for a metal is that it should have a low melting point. The third method for refining the metal is electrolytic refining. This is of more wider application. It is used for larger number of metal ions than or what is possible application of distillation or liquefaction. In comparison to those possible applications, the electrolytic refining has wider applications. The principle is based on the fact that impure metal is made anode and a strip of the same metal is used as a cathode. They are made a part of a cell anode, cathode. This cell is filled with an electrolyte which is containing the same metal which we want to purify. This has electrolyte containing the metal to be purified. Then electric current is passed between these two electrodes. From anode the metal dissolves into the solution and is deposited in pure form as a cathode. Now, what will happen to those which are not deposited on the cathode? They can be divided into two categories. The more basic metals remains in the solution and the less basic metal basically make a anode mud. They are reduced less basic one and they are just deposited on the bottom of this cell and this deposit is called anode mud. The two reactions which are occurring in this electrolysis cell, they are at anode metal is converted into metal ion and free electrons. These free electrons are taken by metal near the cathode and metal ions by the near which are near the cathode and they are converted, those metal ions are converted into metal and they are deposited on the cathode. So, in this electrolytic cell as current passes the cathode becomes thicker and thicker and anode becomes thinner and thinner as the process goes on. I just exemplify this electrolytic refining with refining of copper. Anode is made of impure copper, pure copper strip is used as a cathode. Electrolyte which is used in the cell is copper sulphate. Electrolysis gives electron to copper ions present in the solution at cathode and deposits copper, whereas at anode the reverse reaction happens, that copper ions from the anode goes into solution giving you copper 2 plus and electrons. So, transfer of copper in pure form from anode to cathode happens. You have studied that impure copper is called blister copper. This has a variety of impurities: antimony, selenium, tellurium, silver, gold, platinum. They are less basic than copper. So, they settle, they are reduced and settle at the bottom of the electrolysis cell and called together as anode mud. These metals which are deposited in the form of anode mud basically recovered, and they are expensive. So, the cost of electrolytic refining is also recovered. Zinc may also be refined in this way. If you want to refine zinc in a similar way, you have to make anode of impure zinc, cathode of pure zinc, and you can use zinc sulphate as an electrolyte for this purpose. The third method which is used for purification of metal is called zone refining. In this, basically what we do, if I demonstrate that if you have a rod of impure metal, in nutshell the procedure of zone refining is such that the impurities move in this direction and we make the pure metal to move in this direction. So, after some time there is a divider, left side of which has impurities, right side of which has pure metal, and we cut from here and remove all the impurities. Now, on what principle this zone refining works? This zone refining works on the principle that impurities are more soluble in melt than in solid state of the metal. So, what we do basically, we take a metal rod and in an inert atmosphere we heat it. Why we require inert atmosphere? Because if we use air, the metal may be converted into oxide. So, inert atmosphere is required to keep metal in metallic form. Now, this is heated by two induction coils which are around it as shown in this figure. Now, the principle that impurities are more soluble in the melt. So, suppose these induction coils are here. So, this part is in a molten state of what will happen, the impurities will move into this melt and nearby metal will become pure. So, we start from here and move our heating towards this direction. So, slowly the impurities will be shifted to the left side and pure metal will be go on shifting to the right side. So, we start the circular mobile heater by fixing at one end of the rod of the impure metal, then we move it towards right side, and after some time all impurities are collected around this end and pure metal is rest of the part of the rod. Now, in one go the metal does not become pure using this kind of zone refining. So, what we have to do? We have to repeat it. We have several times. So, after repeating this kind of heating several times, the metal becomes slowly pure and pure, and the impurities are collected on one end of the rod and the another end of the rod or the major part of the rod becomes of pure metal. What we do? We can then cut out the zone which has impurities and use the remaining purified metal. This method is useful for making semi-conducting materials of high, for example, germanium, silicon, boron, gallium, indium. The next method is vapor phase refining. This method is first used for nickel. The principle of the method is based on the fact that metal can be converted into a volatile compound and collected as vapors. So, metal impure, it is reacted with something so that Ma which is formed is volatile in nature. The presumption is that in a impure metal only metal interacts or reacts with a resulting volatile metal. In other impurities do not show this kind of reaction. Now, so metal specific which we want to purify is converted into a volatile compound and this volatile compound is decomposed to give pure metal. So, for applying vapor phase refining, the two basic requirements are it should give a volatile compound first and the volatile compound should be easily decomposable. These are the two basic requirements. So, it should have a reaction which converts it into a volatile compound and the volatile compound is decomposed to pure metal. Volatile compound with an available reagent and second is it should decompose. Otherwise, recovery by this method will not be easy. As I told you that for the first time this vapor phase refining was used for nickel and the process is called Mond's process. Nickel, if it is heated in a stream of carbon monoxide, it is converted into nickel carbonyl or more specifically nickel tetracarbonyl. No other metal generally found as impurity with nickel gives any carbonyl when reacted with carbon monoxide. So, the first condition is followed that it has a very specific reaction with carbon monoxide. Now, this volatile complex nickel tetracarbonyl, if it is heated to 450 to 470 Kelvin, it decomposes to give nickel metal. Now, this temperature is not too high and this temperature is not too high. So, at a very low temperature the nickel is converted into a volatile compound and the volatile compound nickel carbonyl is converted also at a much low temperature to nickel back. No other metal shows this reaction. So, this is very specific and is widely used for refining nickel. A very similar method in principle has been reported by von Erkel. It is called von Erkel method for zirconium and titanium. The zirconium and titanium are known to form refractory oxides. So, they have oxygen, they are also associated with the nitrogen compounds or anions. Both of the kind of these impurities which are containing oxygen or which are containing nitrogen, they can be removed by this method. Now, what is done in this method is crude metal is heated in a evacuated vessel with iodine. What is evacuated vessel? A container in which vacuum has been created. This iodine reacts with the metal forming iodides, which are covalent in nature and volatilize very easily or converted into vapors very easily. This metal iodide can be decomposed on a tungsten filament electrically heated about 1800 degree Kelvin. In this case, the temperature is somewhat higher, what you see in case of Mond process with nickel, but it is not easy to remove zirconium contaminated with oxygen containing entities or titanium contaminated with oxygen or nitrogen containing entities, because they are very refractory in nature. So, considering that fact in view, this temperature is considerably good to use this method for refining zirconium and titanium. The decomposition reaction is shown below, where the zirconium tetraiodide is converted back into zirconium and iodine just by heating. The chromatographic methods in principle can be used for refining metal, but using chromatographic separation, the metal cannot be used directly in a solid state form as you have obtained from the ore. The separation is possible of compounds. Separation is possible only of compounds, and the principle of chromatographic separation is that if you have a mixture, you adsorb it on an adsorbent, then pass an eluent or solvent, which when runs through this adsorbent takes away the least adsorbed compound with it. After that, the next least adsorbed compound or ion goes out, and this process go on, and in the end the most strongly adsorbed compound or ion comes out. This process is carried out generally in a column. I just demonstrate. This is a glass column. It is filled with the adsorbent. The entities which have to be separated are put on the top. Then the solvent, which is also called eluent or a gas, if these compounds can be volatilized or can be kept in a gaseous state, when this column is heated, then you can use gas also, but generally it is done with the liquid or solvent. When it passes through this column, the least absorbed comes out first, then the next least absorbed comes out from this column. So, this process goes on. This process goes on because different components which you have adsorbed on the column, they are interacting with the adsorbent to the different extent. Some are strongly adsorbed, some are weakly adsorbed, and as a result there is a separation. So, if you look at this column before coming out of the first compound and you somehow have a coloring agent to identify these entities, then the column has different kind of bands formed or zones formed for different entities. But if you go on running, then these zones will go on moving and getting out of the column. So, to apply chromatographic separation to metal ions, you have to convert the solid metal into a compound. Without that, it is not possible to apply this method. Now, this column apart from adsorbent can be of ion exchange. Ion exchange are of two types: cation exchange or anion exchange. These cation exchange have sodium ions and a matrix which is negatively charged. Anion exchange, ion exchangers have say chloride ion and a resin bed which is positively charged. So, on this cation exchange, if you will pass the metal ion will replace sodium, and when you are converting impure metal into a solution, all metal ions or impurities or mostly of them will be converted into cations. Those cations, they will be having higher binding ability with the exchange resin, and so they will replace sodium, they will bind with resin. So, at the top this will be the situation that resin has metal ions. Now, this situation, if you pass through this an eluent which is say for example, a complexing agent, what will happen? These metal ions will form complex. If I give you an example, EDTA, ethylene diamine tetraesteric acid, these metal ions will combine with EDTA forming complex. This complex formed by different metal ions will not have the same stability, they will be differing in stability. So, those which is forming a very strong complex with EDTA will leave the resin bed and come out as a complex. So, when you will pass EDTA solution, it will run down into the conical flask. After that, the metal ion which has formed next least stable complex, that is the stability of its complex is greater than this one, but lesser than rest of the metal ions, it will make a complex which will run down through this column. Now, in this chromatography there are basically two phases. One is mobile phase, another is stationary phase. In this example, the stationary phase is ion exchange resin. If we are using an adsorbent, then the stationary phase is adsorbent. Mobile phase is EDTA solution which I have demonstrated, or it can be any other solution, or it can be gas also, it can be liquid also, another liquid also. On the left side of this slide, a automatic system is shown in which the solvent is pumped through column and the entities which are coming out, they are detected with the help of a detector. So, this is an automatic system which can be used for separation of the metal ions as well as for detection of the metal ions. Let me take few examples of this kind of separation based on column chromatography. The first thing is that impure metal has to be brought into the solution. Suppose we have brought impure metal into the solution, then the question may be asked, can this procedure separate the kilogram amount of metal ion? Answer is no, it is applicable only to a smaller level of metal ion separation. A small amount can be purified. Very important. Now, so what is the advantage? A small amount of the can be purified, but the advantage is that very closely associated entities or species can be removed from the metal. What are very similar species which are present in as impurities? The best example is that of lanthanides. You know that lanthanides differ very little in their properties, and so properties, if you want to separate one lanthanide, say for example cerium, from other lanthanides, then it is very difficult to use any other method except the chromatographic method or solvent extraction method, which are of in principle of similar type. So, eluents I just told you is a complexing agent. There are large number of complexing agent. It can be chloride, it can be EDTA, or it can be any other organic acid. So, what is separating metal ions? Metal ions are not getting separated by their adsorbing ability or by their ion exchange ability with the resin. They are getting separated because different metal ions form complex of varying solubility with the eluent. The complexing agent which is present in the eluent, it forms of complex of various stability. So, obviously varying solubility, and that is responsible for separation. Now, let me first demonstrate how anion exchange separation or anion exchange can be used for separation of iron, cobalt and nickel or other metal ions. This is based on the fact that the metal ions form complexes. What kind of complexes? Anionic. And these complexes are adsorbed on anion exchanger. In this particular example, iron this kind of complexes will be formed NiCl4 2 minus, FeCl4 2 minus, FeCl4 minus, COCl4 2 minus, COCl6 4 minus. It will depend that what is the concentration of chloride ion which is present. Now, so the complex which is least stable out of these will be easily decomposed if the concentration of chloride ion is lowered, and the one which is stable will remain in the anionic form. So, if we take 90% acetone and 10% 6-fluorohydrochloric acid, cobalt and nickel form complexes which remain stable or which are more stable than the complex formed by iron. But all these complexes are adsorbed on an ion exchanger which is commercially available called Dowex 1X8. So, if you lower, iron is not adsorbed strongly. So, if you lower the concentration of acid, the nickel and cobalt remains in the anionic form, but iron very quickly lose its complex and becomes cationic form, and you know very well that cation cannot remain with the anion exchanger. So, iron comes out first, and after that nickel comes out, and finally cobalt comes out, because cobalt complex is more stable than the nickel complex. This chromatography, which is based on the ion exchange, is called ion exchange chromatography. The naming of chromatography is generally done either using the adsorbent which is used or the technique which is used. If you are carrying out a separation in column, then whatever adsorbent or ion exchange you are using, we call it as a column chromatography. So, this ion exchange chromatography, where cation exchanger reagents are used, is very well known method for separation of lanthanoids, and this is executed in column. So, it is also called column chromatography. Now, the solution of citrate, lactate or the other salts whose anions form negatively charged complex with the lanthanoid are used to wash the ions from the column. Basically, in the column, this is having cation exchanger resin. So, if you pass a complexing agent, then there will be a competition between the complexing agent and the resin for the metal ion. If the complexing agent makes a very strong compound or complex with the metal, with a particular metal ion, it will take out the metal from the cation exchange resin. But if the cation resin strongly binds the metal ion, then complexing agent will be not able to do it, unless the concentration of complexing agent slowly builds up in the column. And this is what happens in case of lanthanides. Lanthanides, they are very similar in charge, which is generally 3 plus. They are also, because of lanthanide contraction, they are very similar in size, but in spite of that the difference in the size is enough for making the complexes of different stability. Now, once a complex is formed, it cannot be held by the resin, it will come out. So, ions that form stable complex, they move off the column, and the one which moves very weak complex, they will come out slowly or later. Those which form stable complex, they will come out first. So, the separation is based on the stability of the complex. So, in general what we can say that cation exchange is not selective, it is not separating the metal ions. What is separating is metal ions is basically the differential complex formation. So, for lanthanides the exchanger just acts like an undiscriminating sponge, that is it absorbs all cations, and real separation is by the fact that these lanthanides make a weaker complex or a stronger complex with the complexing agent. So, this is the summary of the refining methods which are used in isolation of metals.